Okay, welcome to our first video on our impulse and momentum chapter. And to start off, we're going to talk a little bit about, we're going to mix in some things that we talked about that were kind of like kinematics topics and forces topics. We're going to see why they're relevant here and why it's important to talk about impulse and momentum. So imagine that you want to change the velocity of some object, and you want to change the velocity by, let's say, the biggest amount, or maybe you don't want to change the velocity that much. So what sort of factors are going to affect how much the velocity of the object will change? You can do whatever you want to change the velocity of an object. What is going to be important here? Well, seeing as we've done the forces unit, I think probably the most important one that you would say is, well, obviously you're going to need a net force. If you want to change the velocity, that means you want to accelerate something, which means you need a net force. And I think common sense tells us that the larger the net force, the bigger the change in velocity. And that kind of makes sense, because if you have a very big push that you put on something, that object is going to accelerate more, its velocity is going to change more. So we could say that the change in velocity, delta v, is proportional to F net. And remember that when we say delta v, what we really mean is v final minus v initial. Okay, v minus v naught, and it's always in this order. Okay, so that's what we're talking about by delta v, the change in v, the difference between the final velocity and the initial velocity. Now, there are some other factors that could affect how much the velocity changes, what delta v is. I think another pretty obvious one is the time that F net acts. Okay, how much time it takes or how much time that interaction, whatever the interaction is that's producing a net force, how much time is that interaction occurring for? If you have an interaction that takes place over a long period of time, you're obviously going to have a bigger change in velocity than if you had an interaction that took place over a very short period of time. It's kind of like the difference between pushing something for a prolonged period of time and giving it one quick shove. Pushing something with the same amount of net force will produce a bigger change in velocity than putting a net force on an object very quickly with just one quick shove. So we see that more time leads to bigger delta v. So again, we see that delta v is also proportional to the time. One last factor that you might want to think about here is the mass of the object that you are trying to change the velocity of. Be careful when you think about this one, because if you have a more massive object, is that going to make the object accelerate more or less? Think about Newton's second law, F naught equals ma. If the net force is the same in both cases, but you have a bigger mass for one object, that object is not going to accelerate as much. It's going to have a smaller acceleration. Therefore, its velocity is not going to change as much, given everything else is the same. So more mass leads to a smaller delta v. So we would say here that v is not proportional to m, because as m increases, v does not increase. We would actually say that delta v is proportional to 1 over m. As in, if m increases, that's going to decrease, since m is on the bottom, that's going to decrease this entire fraction. Okay, so if m increases, delta v decreases. Now, because we have kind of figured out all these relationships, we can put it all together into an equation. So putting it all together, we get this. Since delta v was proportional to both F net and t, those need to go on the top of a fraction. So I'm going to write delta v equals F net times time. And since it's proportional to 1 over m, I'm going to put that in the denominator of the fraction, m. So delta v is equal to the net force multiplied by the time over the mass. I could rewrite it like this by multiplying both sides by m. M delta v equals F net times the time. So in other words, the mass times the change in velocity for the object is equal to the net force multiplied by the time. Now, last year when you took Regents, we derived this a slightly different way. This is still an absolutely fine way to do this. I want to focus on this chunk of the equation right here, m times delta v. What we're really referring to here is some object that is having its velocity changed, okay? And I'm going to make it actually slightly less complicated for a second. What if we just had an object that was moving at some velocity? When we have an object that has mass, all objects have mass, that's moving at some velocity, we say that it has momentum. So the definition of momentum, it's kind of a strange one. It's a quantity that represents what I like to call an object's motion. An object that is in motion has momentum, an object that is not in motion does not. It's not just how fast is the object moving, it also takes into account the mass. The symbol for momentum is P, and the equation is P, the momentum, equals m times v. You've probably heard me last year, I made the bad joke that why is the symbol for momentum P? It's because there's actually a silent P in front of the first m in momentum. Okay, that was one my college professor told me. So I like to always pronounce it whenever I see it. I think of momentum. It's kind of like the silent P you see in pneumonia or pneumatic. Anyways, the momentum is given by m times v. And another question you might ask is, well, why do I care about that? Okay, why is this important? Why are we taking the mass and multiplying by the velocity? And the best answer is because it is useful in certain situations to do so. Okay, someone had to come up with this. I'm not saying that momentum is not real. What I'm saying is this relationship is not an obvious one. And it took someone actually doing science and experiments in order to figure out that, hey, this quantity, if I multiply these two things together, seems to be important. That's why we study momentum. Also notice that this equation, P equals mv, m times v is very similar to this, except there is a difference. Okay, you can't just ignore this triangle. That triangle is a delta, and it means delta v. Okay, it means change in velocity. So momentum, by itself, just the plain old momentum of an object, is m times v. This quantity is a vector. The fact that we're using velocity and not speed here might have given that away. And the units, as you can tell from the right-hand side of this equation, are mass is kilograms, and velocity is meters per second. So we have kilogram times a meter per second. Kg times m over s. Okay? So momentum is m times v. An impulse is not the same thing, but it is very, very closely related. An impulse, the word definition, is a change in an object's motion. So that right there tips us off that if momentum represents motion and impulse is a change in motion, then you might get the idea that impulse is actually a change in the momentum of an object, and that is exactly right. It is the change in an object's motion caused by a net force acting over some period of time. Okay? So, if an impulse is a change in momentum, that means it's equal to this. M times v would be just an object's momentum. M times delta v, well, that's an object whose momentum is changing. The momentum is changing because the velocity is changing. We're not really going to deal with objects where the mass is changing, although that is possible. We're just not going to deal with very many of them, if any at all. So m times v is momentum. M times delta v is an impulse, which also means that an impulse is also equal to the net force multiplied by the time. So I have this kind of string of equations that I can write. J is the symbol for impulse. It's equal to F net times time, and it's also equal to m times delta v. An impulse, just like momentum, is also a vector, and it also has units of kilograms times meters over seconds. Or, since it's also equal to a net force multiplied by the time, net force is newtons, time is seconds, you could also say that the units of an impulse are in newton seconds. Matter of fact, you can say that for momentum too, since the units are the same. Kilogram times a meter over second is the same as a newton times a second. Okay? Same units as momentum. So we've kind of touched on this already, but the relationship between these two, the relationship between impulse and momentum. Since P equals m times v, then delta p, in other words, a change in momentum. How do you change an object's momentum? You change its velocity. You could change the mass, but again, we're not really going to deal with that. That's a little more complicated. Delta p must equal m times delta v. M is a constant. We're going to keep the mass constant. We're just going to change the velocity. It's the easiest way to change something's momentum. Mass doesn't usually change. Okay, so putting this all together, if delta p equals m times delta v, then I have this big, long equation that I can write down, and I can show you how to use different parts of this in different situations for problem solving. J, in impulse, is equal to the net force multiplied by the time on an object, net force on an object multiplied by the time that the net force acts. That's also equal to the object's mass multiplied by its change in velocity, and that is also equal to just an object's change in momentum. All of these terms mean the exact same thing. Impulse does not equal momentum, but an impulse is equal to a change in momentum. Very similar to how an acceleration is not a velocity. Acceleration is equal to the change in velocity over time. Okay? In this case, an impulse is not equal to momentum, but the impulse is equal to the change in momentum. Let's do one example where we put in where we use this numerically. We use this set of equations to solve a problem. An object with a mass of 5 kilograms has an initial velocity of 7 meters per second east. It experiences an impulse of 15 newton seconds to the west. What is the object's final velocity? So my tips for dealing with questions like this. Okay, this is a question, at least the basis of this question you might see very commonly on a multiple choice. My suggestion for this is pick what you need from the equation and then solve. You don't need to write down that whole equation every single time. That would be crazy. What you do need to do is identify what is given to you in here, what parts are useful, and then solve. We want to know the object's final velocity, v. We know the initial velocity is 7 meters per second east, and note that word east. We are also told that there's an impulse of 15 newton seconds west, and we're also told the mass. Now notice that we're given directions here. Okay, sometimes you'll be given directions. This is a vector quantity. If quantities are in opposite directions, all you have to do before you start the problem is pick a direction to be positive. It's up to you, just like with setting a coordinate system. Pick a direction to be positive, and then the opposite direction must be negative. So in this case, and a lot of us just kind of, we kind of do this anyways. In this case, what we're going to do is we're just going to say, and you don't have to do it this way, you can do it the other way and it'll work out the exact same way. Let's pick our positive direction to be east, and if you don't believe me, try it. Which means anything to the west must be in the negative direction. I know impulse, I know mass, I know the initial velocity, I'm looking for the final velocity. What that's going to lead me to is this, J equals m delta v. And yes, you should write delta v first. I'm going to expand this to J equals m v minus v naught. And now I'm going to plug in. The impulse is to the west and it's 15 newton seconds. Remember, I said west is negative, so that needs a negative sign in front of it. The mass is 5 kilograms. The final speed is v. The initial speed, which goes second, remember it's always v minus v naught, is 7. So I'm going to do minus 7. And I don't need to put an extra negative sign because that east direction is positive. I do have to have the minus sign because that's what delta means. It means change in, or final minus initial. But I don't need to put another negative sign in there. Okay, let's see, doing some quick math here. Let's see, I keep 15 on this side. 5v I'm going to distribute minus 35. I add the 35 to both sides, plus 35, plus 35. I end up with, I'm going to bring it up here. Let's see, that's 20 equals 5v. So v must be equal to 4 meters per second. Notice that it's positive. Since our answer is positive, the direction must be east. And that's nice. You don't have to worry about whether it's positive or whether it's east or west, because the answer tells you. Since you said east was going to be positive, then therefore if your final answer turns out positive, guess what? The final velocity is to the east. If it had turned out negative, you would have known the final velocity is to the west. So I'm just going to add in east down here, just to clarify. You don't have to, but I like to do that just to make sure that we all understand. Now, had I picked east to be negative, watch what would have happened. West would have been positive. This would have been a positive 15 newton seconds. 5 kilograms, that wouldn't have changed. V wouldn't have changed. I would have had minus a negative 7, because then east would have been negative. I have the minus sign from the equation, and then I have to put another negative there. I would have ended up with 15 equals 5v minus 30. Oh, wait, hold on a sec. Oh, no, it would have been 15 equals 5v. Let's see. V minus a negative 7 would turn into plus 7. 15 equals 5v plus 35. I would have subtracted 35 from both sides. 15, should have been doing this. 15 minus 35 is negative 20. I divide by 5, and I get negative 4. Well, wait, that's different, you might say. Well, if I made west positive and I got a negative answer, then that would indicate that the final velocity is to the east, which is exactly what we got in the other case. Okay, so the direction that you pick to be positive doesn't matter, but you do have to pay attention to it because it can give you information, and it will give you information about the final answer, what direction the final answer is in. Okay, I'll come back in a little bit and we'll do the back side of that set of notes.